We're now ready to look at piecewise functions. So what are piecewise functions? Piecewise functions are a way of combining two or more functions that are defined over specified domains. A common example that many of us know of a piecewise function is the absolute value function, a function that returns back a positive value for every input. The mathematical expression for the absolute value function is given here. Notice the bars around the x that indicate the absolute value of x. And the two pieces of this function are return an x if the x you put into the function is greater than or equal to 0, or return a minus x if the x you put into the function is less than 0. Now I'm going to label each of these pieces. I'll label the top one f sub 1 and the bottom one f sub 2 so that we can refer to them easier. The first thing we're going to do with the absolute value function is graph it. And I'm going to start by graphing f sub 2, the negative values of x. And we see from this graph that we have a line with a slope of -1 that goes up and to the left. But notice here I have an open circle at the origin at 0, 0, because this line piece here does not include the point 0, 0, since minus x is only defined for x less than 0. Now I need to indicate that I'm approaching that value, so I put an open circle there at the origin. Now let's look at f sub 1, or positive and 0 values of x. Here the 0 is included, so I have a filled in circle or a closed circle at the origin, and I have a line segment with slope 1 that goes up and to the right. Notice there's no graph here where x is negative, because this piece of the graph is only defined for x greater than or equal to 0. Now the absolute value function combines both of these graphs into one graph, and we see that when we do that, we have a continuous function, a function where in negative values we are moving up and to the left, this is f sub 2, and in positive values we're moving up and to the right, f sub 1, and that hole in the middle for f sub 2 is filled in by the value of f sub 1 at the origin. Now let's consider evaluation of the absolute value function. So what exactly are we doing when we say we return a positive value? Let's take the absolute value of 2. Well, what we are doing is we're looking and saying which piece of the absolute value function does 2 belong to? And we notice that 2 belongs to f sub 1. So we want f sub 1 of the value 2, and that just says return 2 back. If I want the absolute value 0, I see that I'm again in f sub 1, so I want f sub 1 of 0, and f sub 1 says just return your value back, so I get 0. If I want the absolute value of a negative number, say absolute value of -3, I am now looking at the f sub 2 piece of my absolute value function. So I want f sub 2 of -3. It tells me to write down negative x, so I have -3, which gives me 3, the positive value that I'm hoping for. Likewise, if I look at the absolute value of minus pi, I am in negative values, so I want f sub 2 of minus pi. So I have negative pi, which gives me pi, just as I had hoped. So let's look at another example. In our second example, we see a couple things are different. I have 3 pieces here rather than 2, and notice it says 2 or more, so this is another example. And I have a slightly different variable. I'm using t's here rather than x's. If we look at the domains of our functions, g1 is defined from -2 to 0, where the -2 is included in our t values and the 0 is not for this function t squared. The g sub 2 function includes 0 and includes 1 and all the points in between along the line 3t. And the g sub 3 function does not include the starting value of 1, but includes all t values up to +3, and this is also a line segment. So we're going to be graphing first our piecewise function here, and we see here's our graph with the different segments in different colors. So our g sub 1 here is this piece. Remember, I noted that we do not include 0, so I have an open red circle here at 0. I have a closed circle here at t equals -2, which is the value -2, 4. And I included one extra circle, which is the value -1, 1, to help in the graphing of this piece of the parabola that's defined by g1. g2 is a line segment that includes both endpoints, so I include 0, 0, and 1, 3 that are defined by g is equal to 3t, and draw in that line segment. And then g sub 3, remember we said does not include the t equals 1 value, but we approach it, so we must include an open circle at the value 1, 0. And then we have our closed circle, the included value of 3 minus 2, and then we indicate that line segment by connecting those two values. So this is our graph of this particular piecewise function. Evaluation is much like what we did with the absolute value function, only now it's even more important to know which piece we belong to. So we look at g of 5/4 and note that 5/4 is bigger than 1, but less than 3. So we are in g sub 3. We want g sub 3 of 5/4, so we're going to substitute 5/4 into 1 minus t. So we get 1 minus 5/4, which reduces down to -1/4. If I want g of minus square root of 2, I need to determine if minus square root of 2 is in my domain of my piecewise function. So it's helpful to note that minus square root of 2 is a value between -2 and -1. So it falls in this g sub 1 piece of our function. So we want g sub 1 of minus root 2, which means that we need to square this. So we have minus square root of 2 squared. So we can square each piece. Squaring a negative makes it positive, and square root of 2 squared returns back a 2. So that's our function value for g sub minus 2, square root of 2.